This is our first tutorial of quantum mechanics, and in this tutorial we'll head towards the basic mathematical formalism of quantum mechanics. We have already know that what an operator is, how it acts on a certain state, but uh, we might not be able to understand what are the fundamental axioms that makes an operator an operator. In which space does it live? Upon wh- upon which state it can act, what are the outcomes of such an operator, what are the fundamental backgrounds. So, and also an important question, we know that quantum theory is a probabilistic approach to physical phenomena. So if quantum theory is a probabilistic approach, will the operators or the mathematical machinery that make up all the physical features of the nature will also be probabilistic or deterministic? So how to define an operator? So this is the basic task of our first tutorial. And this is going to be a more abstract approach to the mathematical machinery of quantum mechanics. It might be possible that some of you have already been taken the courses of linear algebra and vector spaces in their undergrads, um, um, but there are some people from different backgrounds who will try to do all of the stuff from scratch. So you can interrupt me anytime during the session. So before going directly into the into the into the mathematics of operators, let's start from a very fundamental concepts: how to define a vector in mathematics. We know that we have studied that vector is an object which has both a direction and a magnitude. Within physics and in mathematics, there are a number of objects which neither have a magnitude nor a direction. So can't they classify it as a vector? And if yes, they are a vector, how can we incorporate the notion of direction and magnitude in them? So there are some of the questions that we are going to answer today. So let's start from a very fundamental idea of mathematics, that is vector spaces. So this is from where linear algebra starts. But we will so vector space can be of different types, but we will start from a very peculiar type of vector spaces that is called linear vector space. And so first of all, see what are the features that can be associated with a linear vector space. As I've already told you that we are surely familiar with the arrows from the elementary physics, encoding the magnitude and direction of velocity, the force, displacement, torque, and blah, blah, blah. And we know how to add different vectors. For example, how to add F1 into F2. We know how to add velocities. We know how to add accelerations. We know how to multiply a scalar number by a vector quantity. So a vector space is really a thing which incorporates both of these properties. Uh, so any set of objects that belongs to or that satisfies these two properties will form a linear vector space. But for sure, there are certain restrictions on the definition of vector space. So we'll see what are those restrictions and how to define a vector space in a more rigorous or mathematical notion. So a linear, I'll use basically this Rm symbols. So this is our vector space V. It is a collection of objects. So each and every mathematical entity can be treated as a mathematical object. So an object is a thing upon which certain operations can be defined, which obey certain rules. So this is a collection of some vectors. Now I will not use the general notation of a vector, that is by drawing an arrow on the top of it, but we'll use a peculiar quantum mechanical notion of a state vector, say A. So you might be also familiar with this notion. This is called ket. So now I'm not talking about what a ket is. So this comes from the Dirac notation or bracket notation. So there are some kets, then there are some bras. So these are called technically state vectors. But we'll not see what state vectors is and what is the difference between this notion and this nomenclature. It isn't only a different notation, but it is much more than that. And Dr. Rafi will talk about this at some length later. But we'll only assume that we are talking about this. We'll convert this notation into this notation. So these are our state vectors. State vectors are the things which define the state of a system. As in the first lecture of quantum mechanics, you have seen that in classical mechanics we need two dynamical variables to define the state of a system. That is the position and momentum. So this is a vector which possess these two properties. So these define the state of a system. So a vector which is used to define to express the dynamical state of a system is said to be a state vector. So this is just a different notation. Uh, so a vector space is a collection of objects. Uh, so let me remove this. So vector space is just a collection of vector objects, uh, A, B, C up to Z. These are sketch vectors called vectors, for which there must exist two rules. So there is a rule of addition, that these state vectors can be added. There is a rule of multiplication, that these state vectors can be multiplied with a scalar number. By the way, this scalar number is said to be a field. We'll talk about this in a moment. Uh, these two properties hold some further features of a vector space. And you will see that these are quite quite general to understand what these features are. But let me write all of these properties. So first of there, so these should be closure. So these state vectors will obey the closure property. That is, if V, state vector V, state vector W belongs to a vector space V, then their addition must be closure. Then there should be commutative. V plus W should be equal to, so just let me write all of these quantities. So these should be associative. Suppose we have three elements from the vector space, V plus W plus Z. So addition is commutative, addition is associative. There should be exist a null vector, so such that if you add this null vector into any state vector, it will, sorry, it will yield the same vector. And we'll see in a minute that this null vector must have to be unique. And there should be an inverse vector, so such that V plus into minus V is equal to 0. Plus there is another property, that if a vector is multiplied by a scalar number, so it has to be scalar associative, such that AB multiplied by state vector V. So these are the fundamental properties of the vector spaces or the linear algebra. Usually all of the sets that we deal can obey these properties. For example, the real number is a vector space. Set of all the real numbers. Set of all the complex numbers may form a real space. So may form a vector space. Similarly, all the arrows that we usually study can form a vector space. But the set of all the positive z integers cannot form a vector space, because in all the components uh, or the elements of this set does not possess an inverse. So this cannot form a vector space. So these axioms or these properties are the fundamental feature usually almost all of the theories, whether it is quantum mechanics or it is relativistic point from the relativistic point of view. So if an object satisfies these conditions, that's said to be a vector space. But still there's a question upon which numbers we can define such a space, or what are these A's and B's. So usually this is called a field. I'll not go into the detail formal definition what a field is. But all the numbers that are defining as A, B, C up to X, Y, Z, they are the part of a certain field. This can be real and this can be uh, complex. If a vector space is defined over a real field, over a real set of numbers, then it is said to be a linear and real vector space. Or if it is defined, so this is a real vector space and this is a complex vector space. And if I put something like here, R2, so it means that R is a two-dimensional element. So we are in a plane working, so which is two dimensions. So it is not necessarily important that we always draw dimensions in this way. So this is just on a peculiar basis. And we'll see in a minute what we mean by components or bases in a more abstract way. So similarly, so if there are n dimensions, so this should also be a vector space. So if this field is of complex numbers, then it is said to be a complex vector space. Complex vector space. Usually in quantum mechanics, we deal with the complex vector spaces, but however, both of these are used accordingly. From the definition of these fields, whether it is complex or it is real, we can define some of the axioms. I'm not going to prove these axioms, but these are quite trivial to prove. The first axiom is that null vector has to be unique. Is unique. This is a very important feature. This seems very trivial, but it is one of the most important cornerstones of the mathematical formulation of quantum mechanics. So what does it mean that 0 equals, now remember, there is a difference between this 0 and this 0, or there is a difference between this 0. Although at the moment we are saying that all these quantities are same, but this quantity is more rich in its definition, because this only points about the direction and the magnitude of a vector, but this definition does not incorporate any direction or magnitude, while this is just a number. So there is a difference between all these quantities. Again, I'll reiterate that this is a vector quantity. This is a vector quantity. So by a vector quantity, I mean this lives in a vector space, but we are describing it without including the definitions of length and magnitude. So this is much more than a generic vector. So null vector should have to be unique. Second property is if I multiply any state vector by a real number, by a null real number, then it will collapse to null state. So yeah, in some of the topics, this is also termed as the ground state, but at the moment we are not taking it as a ground state. So this is just a null state of a vector. So there should be exist a unique inverse of a vector. For example, I can write this as, so this is -1 multiplied by the state vector. So this is minus b. So if this -1 is not defined like a field, I can't take this out of the state vector. So this property is coming from the definition of the field. And the fourth property is that this minus v has to be unique, is unique inverse of v, such that minus v prime minus v. So when I indicate a prime over a symbol, it means that it doesn't mean it's a different component of the same vector space. It means that this vector lives in a different vector space, but both of the vector spaces are unique. That is, for example, the same object is a part of two different vector spaces, then their inverse must be the same. So if their inverses are different, then the vector spaces will be different. So for the two vector spaces have to be same, their null vector and their inverse has to be unique. So you can easily derive all of these quantities, all of these theorems. So these are theorems of the linear algebra. So if you at any moment, if you have any question, let me know in the chat box or unmute yourself, or you can speak. So now we have a question that we know that a vector is defined into is an arrow-like object which has magnitude and direction. So can this vector also form a vector space? Does it satisfy all the for example, if we have three vectors, say I vector, j vector, and k vector, does they form a vector space? or does they do not possess a vector space? Or if we have a collection of objects, so that has only the z components, so plus k1 plus k2 plus k3 up to so on. So these are all vector-like objects. Does it possess a vector space, or does it possess a vector space? All the arrow-like objects, this can possess a vector space, but this cannot possess a vector space. Why? Because it has only positive components. There is no inverse in this collection of objects, in this set of elements, so this can't be a vector space. So similarly, if we have a journal matrix, say A, B, C, D, so so there is a set which is a collection of all the 2 by 2 matrices, M1, M2, up to so on. This can also form a vector space, because we know that metric addition is Floyer, it is associative, it is additive. We can multiply a scalar by a matrix. Even it's not only 2 by 2, it can be any n by n dimensional matrix. So inverse can exist, null vector can exist. So matrices also form a vector spaces. So basically, it means that vector can also be defined in terms of vectors. So for example, if I am taking this row, this row can be treated as a vector. Sorry, this column can be treated as a vector. Or if I am taking this column, this row can be treated as a vector. So it indicates that we can define a vector in two different types. So for example, a vector space. So if I, let me call this, let me designate this by this, 1, 2. So either I can designate this vector space as this, or I can also designate this vector space. Let me write an arrow correspondence. 1, 2. So there are two different ways to define a vector. Either we define a state vector in terms of column vectors, or in terms uh, of a row vector. So, so matrices can also be decomposed in different forms of vectors, and we'll see in a minute how much important this notion to us. So this is all from the definition of vector spaces. But these axioms are not enough to compose the mathematical formulation of vectors of quantum mechanics. So from these axioms, we can say that this group of element is a vector space. That group of element does not belong to a vector space. But how can we associate this vector space to quantum-like objects to define all the features of a quantum theory? So to do this, we have to add some extra ingredients to our recipe. So we have to add some different features, and those features will make our vector space into will transform our vector space into a very peculiar type of vector space, which is called as Hilbert vector space. You definitely heard about this space, that vectors, that wave functions live in a special space, which is a vector space. This is a complex space. So this is defined over complex fields. But what are those features which make up a Hilbert space? Uh, so before doing Hilbert spaces, let's do another important thing, which is extremely useful to develop the fundamental formulation of Hilbert space, and that is called the linear dependency or independency vectors. Uh, Basically, it's a theorem of linear algebra. There are certain set of vectors which are linearly independent and which are linearly dependent. Um, so linearly independent set of vectors. If any set of vectors satisfies this relation I from 1 to n, ai defined over a state vector I gives us 0. Remember, this can't be equal to 0, because this is a vector, this is a scalar, both can't be equal. So it must this side must have to be equal to a vector quantity. So that's why I've written this in the but in most of the books, this is written as equal to 0. But there is a but in those books author assume that this is a vector quantity, not a scalar. So even if it is written in this way, it is you must have to be aware that this is a vector quantity, not a scalar, because otherwise it will just make fuss of all out of all of these stuff. So if a vector satisfies this relation, then the set of vectors is said to be a linearly independent set of vectors, or they form a linearly independent set. For example, what do I mean by this? Suppose we have three vectors: one, the state vectors two, and the state vector three. Let me draw these in a more conventional way. So this is one, this is two, this is three. Now I cannot express any of the vector, say state vector 1. I cannot describe state vector 1 in terms of state vector 2 or 3. For example, 1 cannot be equal to any linear combination of this. So it means a vector 1 cannot be described in terms of other state vectors. So, but if a vector, so if I say that this vector can be written as alpha 2 plus beta 3, it means I can define the state vector in terms of other two vectors, or it can be something like this: 1 equals, say, minus alpha 2. I mean, there is if there is any one single, even if there is only a single combination in which a vector can be represented in terms of other state vectors, then it must then it will be a linearly dependent set of vectors. So this is a very important definition from vector spaces or from quantum mechanics. We often have to check that whether our wave functions are linearly dependent or linearly independent. Uh, So if a vector set is if the vector spaces satisfy this relation, then this will be a then this will be a linearly independent set of vectors. Otherwise, it will be linear dependent. So while this is a number, this is a field. This can be scalar as well as complex. So do you have any question? Okay. So for example, let me write another example for matrices. So let me define a matrix I as 0, 0, 1, 0. 1 0 1 1 and vector 3, minus 2 minus 1 0 minus 2. Does these matrices belong to a linearly independent set of matrices or linearly dependent set of vectors? Can I represent any of these matrices in terms of the third one? So just ponder on this for a minute and write your answer in the chat box if you can. It will give help me to give an idea that whether you are understanding all of this stuff or not. So there is a so you can just write yes or no. Yes, Dishan, this is a linearly independent set of matrices. For as there, it can be seen that vector 3 can be written as 1 minus 2 into 2. So this forms a linearly dependent vector space. While 1 and 2 can't be represented in terms of each other. So similarly, we can check any set of a vector whether it is linearly dependent or it is linearly independent. Uh, Now there is a question that if a vector space has n dimensions, so if we have a vector space of n dimensions, how many linearly independent vectors it can accommodate. I mean, how many number of linear vectors it can be decomposed of. If a vector space is composed of n dimensions, because Hilbert space is an n-dimensional vector space. Yeah, so there will be n number of linearly vector spaces, and such a vector space is designated as n of R if it is composed over a real field, or n of C if it is composed over a complex field. But if we have a two-dimensional set of so if we have a matrix, so let's suppose we have a matrix A B C D. How so? This is a two-dimensional matrix. Why this is two-dimensional? Because so this is a vector which has two components. This is a vector which has two components. So this is a two-dimensional. So this is a matrix which is composed of two-dimensional vectors. So in this case, n is equals 2. So, uh, so uh, does this matrix possess two linearly independent or two linearly dependent vectors, or there can be three? Because these A, B can be defined over a three-dimensional space as well. So they say this is A, this is B, and this can be some axis Z. So these two-dimensional vectors are defined over a three-dimensional space. So can I say that this possesses either two linearly independent vectors or three, or there is something else? Okay. Any idea in how many linear independent vectors I can decompose this matrix? So basically, I can
You can decompose them into two. The
in,
information is incomplete. You cannot decompose it into two.
we can decompose it into.
आवाज आ रही है आपको?
जी जी आ रही है.
मैं कह रहा हूँ आप टू डायमेंशनल मैट्रिक्स को थ्री डायमेंशन में स्प्लिट नहीं कर सकते. इंफॉर्मेशन जो है वो इनकम्प्लीट है.
हाँ, तो हम मैक्सिमम इसको कितने में कर सकते हैं, मतलब कितने हमें
दो में कर सकते हैं आप. मतलब ये सिर्फ प्लेन को स्पैन कर सकता है, ये थ्री डायमेंशनल स्पेस को स्पैन नहीं कर सकता.
So but okay, all right. So we'll see if we can decompose into into three or not. So let me define vector. So it has four numbers. So I can define four vectors in general. So 1 0 0 0. So this is just a very trivial example. 3 0 0 1 0 and 4. So now can any vector can be written in terms of three vectors, three linearly independent vectors, or I need four? So definitely if I write this in terms of three components, I'll miss one of the component, whether it can be this, this, and this. So I can't describe it via three linearly independent vectors. We'll miss a lot of information in that case. So similarly, it can't be described with a two-dimensional vector space. We can't describe it with a five-dimensional vector space. If there are five components, the one component will be a redundant component, and that is completely unnecessary in this case. So this is a two by two matrix. So I can decompose this matrix into a set of four linearly dependent or independent vectors. So basically, this thing A, B, C, D can be written as alpha 1. Sorry, let me call this A1 plus B2 plus C3 plus D4. Now you can easily see that if I miss any of these components, I can't construct all the components of the vectors. So the order of such a matrix is um, n square. So such a matrix will hold n square dimension linearly independent vectors. So if we have a 3 by 3, then there are 9 linearly independent or linearly dependent vectors. So in the case of vectors, that is trivial. So if we have n dimensional space, we can have n dimension n number of vectors. But in case of a matrix, we must have to possess n square number of linearly dependent or independent vectors. I hope it might have cleared the scenario. So let me know if you are still unclear at this point. So this is one of the very important results of the quantum mechanics or the mathematical formulation of quantum mechanics. So this is how we really construct the eigenvalues and eigenfunctions of a system. Uh, and you might do this again in while you will be doing harmonic oscillator. So this is of really very important. These are really very important results in the case of harmonic oscillator. So any vector in an n-dimensional space can be written as a linear combination of n linearly independent vectors, not dependent, and linearly independent vectors. Okay. I now introduce another definition in the concept of our vectors that uh, in classical mechanics or in Euclidean space, we talk about the components and the unit vectors. So similarly, we can decompose a vector into the coefficients of expansion and certain bases. For example, if I write a vector as, so this is my state vector, how can I expand this vector into its components and into a some bases? So I from 1 to n, this can be written as vi. So this is called the basis. So this is our basis vectors. This is state vector, which is describing the state of the system. And this is called, these are called the coefficients of expansion. So you can think of basis vector as a coordinate system. So for example, there can be, so if I draw this coordinate system, so this is x, this is y, this is z. We know that all of these vectors are at 90 degrees to each other. So basically, and they point in certain directions. So this is in I, this is in j, this is in k. So IJK form a basis which are orthogonal to each other. So this basis is said to be an orthonormal basis or orthogonal basis. So so vector can be spanned over some bases. For an n-dimensional vector, so if a vector has n components, we need to have n-dimensional space, n-dimensional basis. So this is how we can decompose a vector or expand a vector into its into a basis. So now now there's an important theorem about this quantity, this expansion, that this equation has to be unique. If again, you can think of this in a sense that if we say that vector is not unique, then the fundamental theorem of special relativity can be violated, which states that all of the laws of physics has to be invariant in all frames of references. So you can think of basis vector as a frame of reference, although this is a vague explanation of the term, but you can visualize it as a frame of reference. So in different frame of references, results should be the same. If or in the same so, or if we are working in the same coordinate system, say x, y, z, then these basis vectors has to be unique. This expansion has to be unique. So by unique, we mean that this component has to be same. So vi should be equal to vi prime. If we are working in the same basis, so in a different basis, I can expand this state vector as vi prime. Now remember, I have kept the basis same. I can't change the basis. If I change the basis, the coefficient of expansion will automatically be changed. Now let's multiply this by a negative sign and add these two expansions. So this will yield a zero vector, and here we have vi minus vi prime I. So this can only be, so right hand side will only be equal to 0 if this term is equal to 0, which shows that vi equals vi prime. Sorry. So this is one of the most important theorems of the quantum mechanics. So given a basis, the components are unique if the base is same. But if we change the basis, the component will change. So you have to be very careful while doing the calculations in quantum mechanics, that even by mistake you are not committed to change the basis. So, and this happens when you have to switch from position basis to momentum basis, or momentum basis to position basis. So given a basis, the components are unique. Now using this, now there is another question which arises, that if a vector element obeys the axioms of a vector space, then the basis vector should also obey the axioms of the vector space. So if I say that this vector, these two vectors belong to a specific vector space, then their corresponding basis vectors should also obey the axioms of this vector space. And we can easily show this, and and if at and if they follow the axioms of vector space, we can say that by adding two vectors, we mean that we are adding their components. So these are just their components. So they are the parts of their components. So let's expand v in a basis I. Sorry, it has to be I w. Let me expand it in the same basis. So v plus w I vi. Sorry. So this is I wi. So this indicates that when we say that we are adding vectors, technically we are adding the components of the vectors, the components which are spanned over some basis, and the basis is given in terms of this I. Similarly, we can define all the other properties. The second important property of the vector space is that if a state vector is multiplied by a scalar number, whether it's a real or a complex scalar number, so vi, it can also be written as. So the basis vector also obey the properties of the vector spaces. To multiply a vector by a scalar, multiply all the components of the vector by a scalar. So this is all from the basics of the vector spaces. Uh, but but till yet we did not speak even about the notions of lengths and the angles. So we did not speak even a single word about these two notions. So without these two notions, we cannot define different operators. For example, it is customary to define the spin of an electron in quantum mechanics, and spin is something which can be associated with the peculiar type of rotation. If there are no if there are no angles, there will be no rotations, and if there are no rotations, we cannot describe a quantum mechanical feature of a system in terms of vector spaces. So vector spaces must also accommodate the notion of uh, lengths and angles. So to define angles, we have to add some extra features to our conventional vector space, and that feature will make this vector space as an Hilbert space. So now we are turning towards Hilbert space, and we'll see that how Hilbert spaces makes operators different from conventional arrow-like vectors. And the idea of this circles around a very important concept of inner product. I'll not call this like a scalar product because this is something different from the scalar product. Although, although we can rename scalar product as an inner product, but technically it is something different from the conventional scalar product. So there are some features which cannot be studied in conventional scalar product. Usually, a scalar product for two arrow-like vectors can be defined as a dot b equals a cos of theta. So where theta is the angle between the vectors, and this can also be written as ax bx plus up to so on, az bz. And there are certain features which are associated with this vector, with this scalar product. That is a dot b dot a. So order does not matter, which shows that this is a symmetric. A dot a can be greater than or equal to 0 if and only if vector a is 0. So this is called positive semi definiteness. So if a vector is 0, then the dot product either will be 0. Um, Plus it is linear in second vector. So a dot b b plus c equals b a dot b plus c a dot c. So this is the property of linearity. Uh, so now we will generalize this result in terms of vector spaces. So first of all, we'll change the notation. In mathematics, in mathematical sense, this is written as, so if I'm talking about these two vectors, I can write these as a comma b. These are just parentheses. But in a Dirac notation, it is written as a b. And this is not equal to a dot b. So what are the features uh, of of inner product in a Hilbert space? So first of all, order matters a lot. So I cannot write this thing as b, as I can write it here. So if I have to do this, I have to put a complex conjugate here. So which indicates this is skew symmetric. Inner product is skew symmetric in Hilbert space. It is not symmetric. So it does not possess any linear symmetry. Plus the self dot product will be um, if and only if vector v equals state vector. So it doesn't mean that if you multiply a vector by a scalar number, then it will just be 0, or these two vectors are orthonormal, then it will be 0. So the state vector must have to be 0 itself. So this will be, if the state vector is 0, then the condition of positive semi-definiteness will be observed. Uh, since inner Hilbert space, or the inner vector space is not symmetric, so we cannot define the linearity. So we cannot say that linearity on the first or the second operator will be the same. For example, uh, if I can write this thing as um, plus b d dot c a. Just remove this. A dot c plus b b dot c. So it doesn't make any difference how can I multiply all these numbers. But in a Hilbert space, I cannot define this relation as it is because this is skew symmetric. So this linearity can only be described for the second operator, for the second vector, not for the first vector. For example, I can write this as v A into W plus B is third vector Z plus B V C. So this is linearity in ket, or or the second operator. And this won't be linear for the bra or the for the first vector for the first operator. This has to be anti-linear for the bras, because of state. So order matters a lot in quantum mechanics. So this so now you can easily think that why do we need a commutation in quantum mechanics? Why order matters in so as the order matters, so we need a commutation relation. So this is anti-linearity in bras or the first operator. So this is because of skew symmetric nature of the vector space. Again, this property is very important in our physical phenomena. So this indicates that this self dot product, self inner product, is not just real, but also positive semi-definite, and it vanishes only if the vector itself vanishes. Otherwise, it can't be zero. It can't be zero if two vectors are just orthonormal to each other. So there are certain conditions which can be imposed. Uh, so for two orthogonal vectors to be zero, but the general condition is that the inner product will only be zero if and only if the vector vanishes itself. Not just by not, it can't be just by multiplying it with some scalar number, which is zero and will make the vector zero. This can't be true. Okay. Um, So, but by some means, if we say that the inner product of two vectors vanishes, then we can say that these are two orthogonal vectors. And again, this will only be vanished if any of the vector vanishes itself. And the norm of a vector can be defined with the relation. These are just the features of the inner product that we are used to talk in conventional algebra. So this thing will make a wave function normalized wave function. So normalized wave function will always have a unit norm. Norm means length or the magnitude or the scaling factor in a loose sense. This can also be treated as. And if we have a basis vector which has unit norm, then such bases are called orthonormal bases. Usually we love to do quantum mechanics in orthonormal bases. It just swept away all of the technical difficulties. For example, the conventional IJK. These forms these forms an orthonormal set of bases. So similarly, so now we have to devise a concrete formula like A dot B equals AB cos theta for the set of vectors in terms of the bases. So define a state vector I, Vi, I. Now I'll define this another state vector J into some different bases. And what I have to do, I have to find V with this W. So, so this will be I, the complex conjugate, as we have defined it as we defined it to be skew symmetric, and this will be I. So there will be double sum, one on I, one on J. So Vi So this is just a number, so it doesn't matter whether I am putting it to the right of the W or to the left of the W. So Wj I j. So this is technically the definition of an inner product or the dot product in vector spaces. So to know the dot product, we have to know what this quantity is, and we know that this, and it depends upon the details of the vector of the basis vector. If we know what is the relation between I and j, we can easily define this quantity. So that's why so this can easily be figured out if we define these basis vectors as to be orthonormal basis vectors. So from the condition of orthonormality, so if these two basis vectors are orthonormal, then I, j will either be equal to 1 or 0. These will be equal to 1 if I equals j, and these will be 0 if I does not equal to j. So that is Kronecker delta. So now I can write this as a single sum, or so let me write it like double sum at the moment. Vi star Wj Kronecker delta. So Vw can be written as a single sum now. Vi star W, sorry, Wi. In orthonormal basis, this will be our starting point to find the notion of an inner product. So now we can easily now we can easily find out the self dot product or the norm of a vector. V so I Vi star Vi. So this will just be I Vi square, and we can see that this is either 0 or can be greater than 0. It can't be negative. So this is how a dot product preserves length. So this is how dot product preserves the conventional properties um, of the vector spaces. So if we choose uh, but if we choose a different set of basis vectors which are not linear, so remember, when we talk about that this is orthonormal, so then these are also linearly independent vectors. So these are linearly independent vectors. So you can see that linearly independent vector, the choice of a linearly independent basis will make mathematics much easier than a non-orthonormal components or a linearly dependent set of vectors. So it is always our preference to work in a linearly independent basis. However, we can also however we can also construct linearly independent vectors from any set of vectors, even if we do not have any. So I will not go into the details, but you can look for it in any of the books. There is a theorem that is called Graham-Schmidt theorem, that how to construct linearly independent set of vectors from an orthonormal. Uh, so. Uh, Sorry, basically this theorem is used to construct an orthonormal basis from a linear combination of basis vectors. So if we have a if we have linearly dependent or linearly independent vectors, so this theorem will elaborate how to construct an orthonormal basis. So once we are done with constructing a linearly orthonormal basis, then rest is just calculation. Uh, before defining an operator, we have to define two or three more results. The first result is for dual space or a dual vector. So as I have told you earlier, that we can write a vector like this or like this. So, and if I'm talking this as 1 2 3 up to n, then I can also write this as. So these are just different ways to write a same vector. So that's why these two are called duals. So a vector v is the dual of this. So this ket vector is a dual of this bra vector, and this bra vector is a dual of this ket vector. But I cannot say that these are two equivalent. Although in real spaces, in real vector spaces, they can be equal, but in complex Hilbert spaces, they can't be equal. Why? Because we know that again from the definition of inner product in vector spaces, VW is equal to WV statistic. So this is equal to this. So this is a complex. So this is technically the complex conjugate. So such a space is called dual space. So if we say that this vector lives in a Hilbert space, then this will live in a dual Hilbert space. So we can construct a dual Hilbert space from this space. We can construct a normal Hilbert space from the dual space. We can transform between all of these vector spaces, and there's no. So this is just like a twin. So we have, so nature gives us two different ways to do calculations. In relativity and quantum mechanics, and such spaces can be defined as um, uh, dual spaces. For example, you know that from Maxwell equations we can write all of the laws from the we can write all the laws of electrodynamics just by from the definition of electric field, and we can write all the laws just by the definition of magnetic field. Although there are although there are certain features, or there are certain there's a preferred procedure which allows us to do so. So but we can construct the theory of electrodynamics either from electricity or from magnetism, or in relativistic electrodynamics, I think Griffith's 12th chapter, you can see that magnetism is nothing but just an outcome from the marriage of electrostatics and relativity. So it indicates that magnetic force can be dual to electric force. So that's why it is customary to write this relation as. So these are just two dual fields. So as these are the two dual fields, they say these are two dual spaces. So it doesn't matter whether we are working in a normal space or in a dual space. These are just different ways to write. But the convention is a state vector, a ket state vector is represented in column vectors, while a bra vector can be represented in rows. So now it will also make our notion more clear that when I multiply a row vector by a scalar vector, I'll get some number. But I cannot multiply this column vector, this this row vector. So this is not possible from the usual matrix. So that's why we write this as. So when we talk about this complex conjugate, it means that this has to be a row vector, or this has to be a row vector. Otherwise, we can't multiply this thing. So anything which is on the left of a notation is said to be a row vector, and anything which is on the right is said to be a column vector. So otherwise, we can't get a real number. And if we can't get a real number, we can't do anything in quantum mechanics or in field theory. So similarly, we can also uh, expand a vector in orthonormal basis. Sorry. So for example, a vector is this. Thus, a vector can be represented as I, vi. So this vector is expand in the ith basis, and I want to find. So suppose this is our ith basis, and I want to find this jth component in this basis. So how can I find the jth component in x basis, or how can I find yth component in x basis? So say you want to find axy. So how can I find this component? I just have to dot it with our state vector I, vi, j, I. So this can also be written inside the state vector because it's just a number. So I have put it down here. So this is I, vi, this is Chronica delta, j, v. So what this will yield? This will yield. and Vj is the component, it's a jth component. This is the ith component in the ith basis. If I want to find the jth component in the ith basis, I'll just have to dot it with j basis vector. So when I put this relation back in the original equation, I can define a very important result, that this is how to find a jth component in the ith vector, or um, or how to expand a vector in self basis. So is this clear to everyone that how to find jth component in in I in the ith state? Although this seems quite trivial, that it does. So that what do we mean by this? Is I'll elaborate in a minute that this is just a projection operator. So this is a very particular type of operator. So self projection will make V as V only. So it doesn't make any difference as far as we are concerning about the self components. So, but there is so there are certain features associated with this projection operator, which I will discuss when we will do projection operators in next tutorial. Projection operators are of fundamental importance in quantum mechanics. So similarly, there are adjoint operators. For example, when I say that I can write this as so, what does it mean? This meant that I have taken the adjoint of a ket operator or a ket vector. So these are called adjoint vectors. So AV equals A star. So but if I have this thing, this is just so now if so once I've taken this out of the vector, I can write it here as well, because now it's just a number. So but you can clearly point out the difference um, in the scalar multiplication of bras and cats. So it has to be a complex number. Even if it's a scalar number, it's a real number, then A star will be equal to A. But usually we do not know whether it is a scalar number or it is a real number or not, so we have to differentiate between these two. So this is just the complex conjugates. For example, if we have I omega t, so the complex conjugate will be minus omega t. So this is called adjoint operator, and this is the same thing that we have done in this relation. So we have taken the adjoint of V. So for example, if I'm talking about this, so I have to do this thing. Or if I'm talking about V, I can just write it as. This again comes from the linearity. So, so this is all about the linearity of operators. Even you can easily figure out that there is a rule from jumping from uh, cats to bras and bras to cats. So simply, if you have to take a joint, uh, simply change all the cats into bras and all the bras into cats, and change all the numbers with their complex conjugates. And if there are already complex conjugates, just turn them into UL numbers. So this is how we transform between cats and vectors. So that's so this is a way you can define any expansion. So if I write this as I um, I I V, so similarly I can write this as um, V I. So to take the adjoint of an equation involving bras and cats and coefficients, reverse the order of all the factors. So as I have done this in the equation, and exchange bras and cats and complex conjugates of all coefficients. Okay, so this is all that we have from the vector spaces, and now we have defined vector spaces. we can define operators too. So this is all the mathematical machinery that we need to define operators. Without these tools, we cannot define our, our conventional quantum mechanical operators. So, is there any question? Okay, so should we have to do linear operators now or in the next tutorial? I mean, if it's more, then we can just end this. So okay, so fine. So most of the people are saying that we have to do it in the next tutorial. So next time we will see that how we can define operators using all of the axioms of vector spaces. Uh, okay, so if you have, if there are any questions, I'm open to your questions. So I'm gonna stop recording.